Hello, my name is Nikolai Kumer, and in this video I will show you how to use Simulink. Specifically, I will show you how to implement a PID controller, which is the most common controller out there. Simulink is a programming language within Matlab that allows you to model, simulate, and analyze systems. You can start Simulink in two different ways. You can either navigate to the Home tab and click the Simulink button, or you can type in Simulink into the command window and press Enter. You will then be presented with the Simulink Start page, where you can open and load existing models. We're going to start with a blank model, so we click Create Model. Now we're presented with the blank model canvas. To begin building your model, click the Library Browser button. Within the Library Browser, all of the functions that are available to you are organized. Here you have some logical toolbox groupings, and at the very top you have some standard libraries. Simulink wraps every function around a function block. It can have multiple inputs, or it can have multiple outputs. There are also sources where a signal can originate. For example, if you want to simulate noise, a ramp input, step input, or a sine wave, you would find them here. There are also sinks, which is where a signal can end up. The scope will be most important for us. Let's begin building the first open loop model. Navigate to Simulink and then Continuous and find the transfer function. You can either click and drag the block onto the canvas, or you can right-click and select Add Block to Model Untitled, where Untitled matches your currently open model. We're also going to need a source for the signal, which will be a step function. And we will need to display the signal that comes out of the transfer function, so we'll use the scope. Drag all of the blocks apart. To connect the blocks, select the output of the step function and drag it over to the transfer function. And we'll also connect the scope block as well. If for some reason you did not fully connect it, the signal remains red. Now let's define the transfer function. Usually you would get the transfer function by modeling a system from first principles, or if you have an existing model, you can run a system identification and then get a transfer function using the output data. Double-click on the transfer function to bring up its properties. The numerator coefficients are a vector of the order of s. The system that we want to simulate is 1s squared plus 6s plus 10. And in the denominator, we want to simulate 1s cubed plus 0s squared plus 7s plus 1. At the moment the block is too small, so you're only shown numerator and denominator. You can resize the block until the actual transfer function appears. Verify that this is exactly what you intended to simulate. Now let's double check the properties of the step function. Double click to bring up the properties of the step function. The step time is the time in seconds when the value changes from 0 to the final value. These settings are alright. We also want to simulate the model for 20 seconds. When we are ready to simulate, we press Run. At the bottom you will see a bunch of status messages. When the message says ready, the simulation is complete. Double-click on the scope block to see the output. This might take some time. You can see that the signal starts to oscillate and increase. When you're in this view, you can use the zoom function to either zoom, pan, or zoom in the X. Let's zoom in on the X. The output of the transfer function is 0 when time is less than 1 second. That's because of the step function. The value is 0 there. If you want to return to the original view, you can go to the Scale option and then rescale the entire view. You have now simulated your first open loop transfer function. It is generally a good idea to rename all of your functions and all of your signals. Let's rename the step function to be the input. Our transfer function will be the plant, and our output scope will be the output. The input signal I'm going to call v of t. Let's assume that the transfer function is something like a DC motor. Then the v of t represents the actual voltage that is applied into the DC motor. The output signal I'm going to call y of t. And in the DC motor example, this could either be the position or the velocity. Next up, let's add feedback to the system. I'm going to go back to the library browser and grab a summation junction from the commonly used blocks. You can disconnect blocks and signals by holding Control and then separating them. We will need to configure the summation junction. Double-click on it to bring up its properties. The list of signs starts at the top and goes counterclockwise. If, for example, I replace the vertical bar with another plus sign, then the plus sign will appear at the top. We need to make this a negative feedback loop, so I'm going to configure it as follows. And I will also reconnect all of the signals. I'm going to rename the signal that goes from the input to the summation junction u of t, which is a commonly used convention for input signals. And I will take the negative feedback branch and connect it to the output. We can now run the simulation. Double-click on the output to visualize the system. Select the autoscale function to see that at time t is equal to 1 second, the system kind of oscillates around some value, which is approximately 0.9. You have now simulated a closed-loop system. The currently simulated system is a feedback loop with unity gain because there is no gain block. Let's go back to the library browser and grab a gain block. I'm going to name it KP, and we can click and drag it in between the summation junction and the plant. I have previously tuned this controller, and a value of 5 is roughly appropriate. You can play around with those numbers and see how that affects the response. I'm going to rename this signal E of t. The E of t will represent the difference between the input and the output. And I'm going to call this block V of t, which is still the input into the transfer function. Let's simulate a system and double-click on the output block to see what the resulting signal is. Since we named the signal, it actually shows you y of t right here. And you can see that there is some overshoot and some oscillation, but then the signal settles into some steady-state value. You can find out what the steady-state value is by actually zooming in. It's roughly 0.98 something. The only thing about this response, though, is that it currently does not show us what the desired input is. Let's fix that. Let's go back to the library browser and grab a mux block. A mux block is essentially a block that combines multiple signals. You can double-click and select the number of inputs, and 2 should be just fine for us. I'm going to disconnect the signal and put this block right here. And I will connect it to the output block. And then the next thing I'll do, I'll take the second signal and connect it to our input block. This will show us our desired input. Now when we simulate a system and double-click on the output, we actually see our desired input and how the system responds to that desired input. we now have created a PID controller of just the proportional gain. The current system represents unity gain feedback loop. I'm going to add proportional control. Navigate to the library browser and grab a gain block. We're going to call this KP, which is the P in the PID controller. We'll put it right before the plant, and we're going to rename this signal to E of t, which is the error between our desired input and our actual output. I'm going to also call this V of t, which still represents the voltage, for example, into our transfer function. I'm going to tune up this gain to about 5 and simulate the system. Now when you take a look at the output, you see that there is some oscillation, but eventually the system ends up settling into some steady state. We can zoom in and find out the exact value of that steady state, which is 0.98. Currently the scope block does not display the desired input, so let's fix that as well. We can go back to the library browser and grab a mux block. A mux block essentially combines multiple signals into a vector. You can double click and configure the number of inputs that you want to display. 2 should be sufficient for us. We can disconnect this output block and put it right here. And we'll reconnect everything. And I'm also going to connect our desired input. Now when we simulate a system, we now see 2 signals on here. The yellow one is our actual step input, and the blue one is the actual response of the system. Now it becomes a lot more apparent that we have a steady state error, so the proportional control is not sufficient, and we need to start looking into the I and the D of the PID controller. The integral portion of the PID controller is perfect for systems that have a steady state error. This is very common for systems that have a lot of friction, where the purely proportional gain is not sufficient to drive the error to 0, but gets stuck somewhere just shy of 0. We're going to go to the library browser and grab an integrator block. I'm going to rearrange a few things because I will need some space. In Simulink, if you click and hold Control, you can create a copy of any block. I'm going to call this Ki, which will be the integral gain. I'm going to connect the input into the integrator to our error, because it will integrate the error over time. I will also need another summation junction. And I'm going to configure it to have 3 inputs. I'm going to delete the signal and add it right here. None of these signals are V of t anymore. We have defined V of t to be right here, just before the signal enters the transfer function. The way that the system is set up now, we have our input into the plant is a combination of the proportional and the integral gain. So let's run the system now and take a look at the output. You'll see that the steady state error has disappeared because the integral action integrates the error over time and adds more effort into the system to drive it to 0. We do, however, have a lot of overshoot. This is where we can use the derivative gain. Let's go back to the library browser, go back to continuous, and add the derivative block. We will also need a derivative gain, which we generally start with a low value first. This is because derivatives can get quite large. Now when we run the simulation and look at the output is actually quite good. We have no steady state error and the overshoot is quite reasonable. I encourage you to play with the gains to see what kind of effect they have on things like overshoot, settling time, and the steady state error. The addition of the derivative block actually caused Simulink to throw a warning. You can view them right here. The solver encountered an issue at time t is equal to 1 second. This is when the step input went from 0 to 1, causing an infinite change in the derivative block. You can address this in a couple of different ways. One method is to add a filter right at the input to make sure that the corner here is a smooth one. What is more commonly done is actually the addition of a filter right before the controller to smooth out any random noise that you will have in the system. We're going to deal with it in a slightly different way because it's related to the final step of controller design. At this point, we have tuned Kp, Ki, and Kd, and we have verified that our output is within some sufficient parameters. What we have not done yet is verified whether the input into the plant is achievable. Let's create a new scope and call it TF input. And we'll connect it right here. After we simulate and take a look at the output, you can see what the problem is. The controller is requesting an infinite control input into the system, which causes Simulink numerical errors, which is why it throws a warning. Generally speaking, real systems have real limits. So we can enforce these by using a saturation block. You can use the search function to find them and add them into the model. The saturation block essentially enforces real limits. Think of a DC motor. There is only so much voltage you can give it before the system breaks. We're going to use plus or minus 2. These limits do not need to be symmetrical because some systems can actually accelerate more than they can decelerate. We just need to make sure that whatever our controller sends is within these bounds. Now we can simulate the system again and take a look at the input. After we autoscale, we find that our controller does indeed hit saturation. The addition of the saturation block actually makes this a nonlinear system. However, if the saturation is very short, and if we can verify that our output has not drastically changed, then we can probably assume that this is fine. Let me show you what happens if this assumption breaks down. I'm going to give it a very large input and simulate it again. Now you can see that the controller hits saturation for a much longer period of time. And you can also see that the output is quite a lot degraded. If we can assume that our input is going to be sufficiently small, that our controller does not hit saturation for very long, then we can assume that this controller will work in practical applications. You have now built and tuned a PID controller using its basic building blocks. I find that this is a very important exercise to give you an appreciation for what Kp, Ki, and Kd does inside the actual PID controller. If you lay it out like this, it also becomes very straightforward if you have to implement this on a real system. Take, for example, our DC motor. All you would need to do is measure the output. You then compare the output to its desired input and calculate this E of t term. For the proportional block, you just take the error and multiply it by Kp. For the integral branch, you keep a running total, or integral, and multiply that by Ki. The derivative block, you would need to calculate the derivative of the error and multiply that by Kd. The voltage input into our plant then becomes a summation of all of these three contributions. As a final step in this video, I'm going to show you how to save yourself a lot of time and use the standard Simulink PID controller. Open up the library browser and search for PID. There's two different types, the continuous and the discrete. We need the continuous one. We can create a copy of the plant, and we will need the summation junction. I'm going to try and match up the implementation of this PID controller to the one that we have just created. I'm going to connect the feedback loop and grab the input. Since we're trying to compare something, we will want to display it on the same output scope, so I will need to add a third trace. Before tuning this standard PID controller, I'm going to simulate it first and take a look at the output. The blue trace is the one that we have just implemented. The red one is the untuned standard controller. Let's bring up its properties. The first thing that I would like to draw your attention to is the form. There's the parallel form or the ideal form. Depending on which compensator formula you're using, the P and I will be different. We're going to be using the parallel form. Also, please note that they have implemented a filter inside their derivative term, which we have not. So we will not be able to exactly match the output. So I'm going to set the derivative term to 0. I'm going to set the P and the I to 5. And I'm also going to change this term to 0 as well, so that we have matching controllers at the top and the bottom. Now when I simulate the system, let's take a look at the output. It is pretty close, but not quite identical yet. That is because we have the saturation block that we have not yet considered. Open up the PID controller again and navigate to the Output Saturation tab. We can enable the limit output and set it to 2 and -2. Note that the icon of the PID controller changed to PID plus saturation. Now when we simulate the system, the two traces are nearly identical. I hope that this video helped to introduce you to Simulink and PID controllers. If you have any questions, please leave them in the comments below. Thank you for watching.